lecture which told us plenty of new ideas about cosmic rays. So the next speaker will be, I hope. Okay. Tijana Prodanovic and yeah.
Okay. Thank you. Okay, so we heard we talked more about standard sources of cosmic rays and standard galactic sources, but now I'm going to tell you something a bit more non-standard, and that is possible cosmic ray acceleration in galactic interactions and what sort of implications that would have. And this is, most of this work here is done together in collaboration with my former student, Darko, who is now a PhD student at Marseille. Someone who is on with Dan Milošević here, and Tijana Prodanovic from Georgia Tech. Okay, so,
Levo desno par puta dok on levo.
Par puta.
Desno. Najmanje desno.
Am I out of range, maybe?
I was working for me.
Oh, okay. Okay. Good. The first thing we want to remember when we talk about cosmic ray and particle acceleration and making cosmic rays is, where do you do that? Well, what are the key ingredients that you need? And basically, the only thing you would need are charged particles, shocks, and magnetic fields. And we have many astrophysical sites where you do get all of these ingredients together. So basically, every time you have an environment like that, you are bound to get some particle acceleration and some sort of population of cosmic rays at some level. Now we heard about galactic cosmic rays in this one, but and most of them we consider are coming from supernovae remnants, but more on the unidentified sources and possible pulsar-ridden nebulae galactic sources we will hear later on in a talk from Javan Akatwich. So stay till the end, please. Also, we have evidence piling up that the cosmic rays of the highest energies are coming from active galactic nuclei, through mechanisms we don't yet understand. Also, as Alexandra was talking about yesterday, we also believe that we haven't detected them yet, but we also believe that large-scale shocks that form during the hierarchical structure formation basically are also sites where you do get cosmic ray acceleration and you do get a population of structure formation cosmic rays there. But something that I will be talking about today is something that we started thinking about recently, is the possibility of getting cosmic rays, getting particle acceleration in large-scale shocks that form as galaxies interact, whether they merge or they have experienced close flybys. Those sort of events would cause in the interstellar medium large-scale shocks that we think can result in particle acceleration, and I'm going to be calling those tidal cosmic rays. Like I said, we know that galaxies interact, and we see the effects of these processes the morphology of the galaxies or in some intense emissions, and we see these galaxies twisted and turn due to these interactions. And the effects of these interactions of galactic harassment are more pronounced, of course, on the smaller of galaxies. If you have and that sort of emerges. And like we see in the case of as small Magellanic Cloud, for instance, and so on. And those sort of interactions, galactic interaction, do not only disturb the gas of those galaxies, but we believe also give rise to shock waves, larger scale shock waves, that I would call tidal shock waves. And as a result of those shocks forming, what you expect to get, is heating of the gas and dust, which would again have other consequences on how you observe, for instance, in infrared those galaxies, but also could result then in acceleration of particles. And we do see, for instance, for instance, here what you see in gray is SMC and LMC and Magellanic stream that's formed due to these tidal interactions between these galaxies. Why is that important? What consequences would presence of such a cosmic ray population have? Well, it would cosmic rays. What we know, one of the things they do is they all are included in nucleosynthesis, so they produce light elements. So basically, light elements like lithium, beryllium, and boron, we call cosmic ray emitters. So basically, adding another cosmic ray population in a star-forming galaxy would boost production of these elements and would produce more of them. And what we showed at some point in our singleton model that, for instance, if you consider the case of small Magellanic Cloud, where lithium volatiles were recently been measured in the gas in the ISM, the SMC for the first time, we showed that basically it would be enough to shock the whole gas of SMC twice to explain all the lithium that you see in the SMC. And as Alexandra was saying in her talk, some gamma ray observations also indicate that not all of the lithium-6 in the SMC can be explained in a standard scenario producing them through interactions of normal galactic cosmic rays. So presence of this additional cosmic ray population would be a way to solve that issue with lithium in the SMC, but also would affect the long-standing problem with the origin of the origin of the primordial lithium. Anyway, tidal cosmic rays would definitely affect that. What else would happen if you have this cosmic ray population present? Well, it would certainly affect your non-thermal radiation that you expect in that galaxy. So it would affect a gamma ray and radio spectra of these galaxies, and it would be then tricky to disentangle that emission, like what is coming from standard picture from the standard galactic cosmic rays, and what is possibly coming from these extra population of cosmic rays. So you would expect enhanced synchrotron emission, and that was something that was modeled and seen in taffy galaxies and bridges that form between two interacting galaxies. One other important, and I'll say that, a bit more about that in the next slide, important tool used in astronomy is the well-established correlation that exists between the far infrared and radio emission of star-forming galaxies. So, which is thought to be just purely due to the star-forming process. So you could imagine that adding an extra population of cosmic rays in a star-forming galaxy that is not originating from supernova acceleration of particles in supernova remnants would affect this far infrared radio correlation, and you would want to know that, because we use that to determine soft emission rates and so on. So this correlation, like I said, is something that's been well established, relation between the radio and infrared luminosity, and as we usually represented with this hue parameter, which basically is the ratio between fluxes of infrared and radio fluxes, and this parameter in a larger sample I don't know, 15,000 galaxies or so on, self-orbiting galaxies was found to be about 2.3. And the logic behind that, why you should expect that sort of correlation to exist, is it's all due to star-forming process. Where does the far-infrared radio emission comes from? Well, it just reprocessed UV light from stars, basically reprocessed on dust. So dust absorbs that light and emits it in the infrared. And of course, radio is coming from a synchrotron emission of particles that is accelerated in supernova remnant. So that's the logic behind that, and why we think this correlation exists. Now, the question that we have is how stable is this correlation in a system of galaxies that interact, right? So if really you get some extra particle acceleration when you slide your shocks, this parameter Q, this correlation, would evolve, would change as the interaction proceeds. So we basically wanted then to look into these interacting systems at various stages of interaction. Now these stages of interaction are we labeled by this tumor sequence labeling from stage 1 to 5, so no interaction, the beginning of interaction 2, stage 3 where they form a joint envelope, and finally up to a merger at stage 5. And basically what we did is we took already a pump sample of these observations of the 43 interacting galaxies at various stages of their interactions, and where infrared and radio emission was measured, and we looked at them, and we looked at this Q parameter, that's indication of this far-infrared radio correlation, and wanted to see how this Q parameter, whose nominal value should be here, changes over merger stage through no interaction, so beginning of interaction, maximum interaction, back to the merger into one galaxy. And basically what we found is that early on this parameter increases, which is consistent with with enhanced infrared emission from X-ray heating, then decreases, which is consistent with having enhanced non-thermal emission. It has a synchrotron emission, which would be consistent with the fact that first you get heating from shocks, then you get particle acceleration. It takes some time for this population to build up, and then later on, as this process triggers star formation, you get back to normal. That drives you back to that normal Q value that you expect from star forming galaxies. So we basically expected, and that's what we see on this smaller sample of galaxies, that somewhere, mid-interaction, before the star formation kicks in, the results are consistent with having extra cosmic ray population present that is going to be due to these type of shocks. Now, so basically there is indication that this far-infrared radio correlation varies as the interactions proceed. Now the question is, what happens with this far-infrared radio correlation over the history of the universe, over the redshift? So generally, it is usually assumed that this correlation is stable over redshift. It doesn't change. Its value doesn't change. That there are some models that predict that this parameter, this Q parameter, this correlation should actually vary with redshift. And one of such models was done by Murphy, where he shows that this parameter should actually increase with increasing redshift due to just basically increasing the density of CMB photons and basically making the inverse Compton losses more dominant than synchrotron losses. So basically your synchrotron emission will decrease, which would result in the Q parameter increasing. So there are a few other models that predict that this parameter should actually increase, not be stable over redshift, but increase with redshift. However, places where we could test this would be maybe looking into interacting systems, nearby interacting systems, like M51, and so where basically you have two interacting galaxies, and you would pay more attention to the smaller of the two in a pair, because that would be the one that is more affected, and that is where you will want to see enhanced radio emission, more than what you would expect from the observed star formation rates in that galaxy, and that is sort of what we see in M51, but more observations of similar systems will be needed. Anyway, back to the evolution of this far-infrared radio correlation. Like I said, people were expecting, if anything, that this parameter should increase with redshift. However, recent results of very large surveys in the cosmos field, surveys in the cosmos field, that were recently published, show that basically this parameter decreases, which slowly decreases with redshift. And that was unexpected. That is something that goes in the opposite direction from what you would, if anything, expect, basically. But immediately when we first saw that basically this interaction could potentially lead to access a radio emission, we thought that if anything, this trend, basically as you go to high redshift, your sample of star-forming galaxies would include more and more interacting pairs, interacting systems, which you would not always be able to resolve and to identify as an interacting pair. So your sample would be more and more drawn to the lower Q values. Basically, it would contain more interacting systems, which would have increased radio emission. So this is so this is what we would maybe naively, from the trends that we've seen, naively expect, and so this Q parameter decreases with redshift as your sample includes more and more interacting galaxies, which would have enhanced radio emission. So what I'm going to show you now are really early preliminary results, something that we started playing with, and trying to include all these different sort of effects. This is this is the fit that they found. This is the fit that they found here, basically, and this is basically our model that includes a growing fraction of interacting systems, that includes the predicted increase in magnetic fields and predicted increase in Q parameter. And we also, at this point, I think I included also the cosmic star formation evolution, just because if this extra population of cosmic rays is present, it is competing with galactic cosmic ray population, and if it will resurface, it has to have a stronger flux, and so basically we have to take into account a cosmic star formation rate evolution. So this is just very preliminary, just something we started working on. Something that we also shown in that paper where we analyzed the sample of 43 interacting systems is this far-infrared radio parameter varies over the interaction stage, but we also look in spectral indexes, spectral index of the radio flux in these interacting systems, and so this is spectral index plotted as a function of this Q parameter, far-infrared radio correlation parameter, and different symbols basically are different stages. And what you should notice is here, if it's in this quadrant, it's more non-thermal emission. If it's in this quadrant, it's more thermal. It has thermal emission. And nominally, what people take, just standard spectral index and standard Q, it should be here, everything should cluster around here. But what we see mid-interaction stage, stage 3, these are circles, so they kind of pile up more in the non-terminal quadrant, and later early stages pile up more here. So the spectral index we expect also to evolve as the interaction proceeds. One also other important effect that I want to mention, that's also something we started looking into, it's also at the preliminary stages, is realizing that you would have something like this would also make you wonder about how much you can trust star formation rates being determined at higher redshift. Because if you people basically use just radio observations and the stability of this spiral from radio correlation to determine star formation rates. But if your star formation rate, if your radio emission has this extra piece coming from this extra cosmic ray population, that might lead to overestimate of the star formation rates. So basically, if you want to trust your star formation rates, how you determine them, and you know how to determine them from radio observations or from AH alpha. If everything is well, it should follow this line. But this is all. These are galaxies come together from all interaction stages. So we would want to look at them at different stages. How are these parameters affected? But sample is not large enough, and some corrections need to be taken into account. But the point is, you would want to worry about this, how much you can trust your star formation rate determination from radio observations if there is doubt that maybe systems might be interacting. Basically, my point, the point that I want to make in this talk is to say, to convey this message to you, is that when we talk about interactions and galactic mergers, it's more than just talking about morphology and structural growth. What we need to worry about and realize and to investigate more is the possibility that these processes could give rise to larger scale shocks that would go to the external medium, which could accelerate particles. And in turn, that would affect our light element abundances. That could give us extra non-thermal emissions that can impact the standard far-infrared radio correlation and our star formation rates determination. And basically, if we could get a handle on this, this could possibly serve as a powerful probe of to identify interacting systems at larger redshifts where you cannot resolve that much morphology, so that you have something else to go on in finding interacting systems than just looking into morphology or picking out closed pairs. And basically, to get a handle of that, to be able to do that, we will definitely need a larger sample of interacting galaxies. That is something that we hope to obtain in collaborations with colleagues who work in the Cosmos field. And to first understand this locally in our own backyard, to do some follow-up observations of local interacting systems, and to do some hydro models of actually how these shocks would develop and how long they would live, which is the largest caveat in how they would propagate. So we just barely scratched the surface on this, and there's a lot to be done. And I thank you with that.
Thank you, Tijana, for the lecture. We have a very short time for question, please.
Yeah. Are you sure that shallower spectral index is result only of thermal influence?
It's more of a branched arm sort of signature. right?
But
With
it
larger-
can be a result of efficient particle acceleration.
And that as well, yeah, that as well, yeah.
Okay, we can talk.
That's another thing to worry about.
Okay.
So, one more question, please, if you have.
And especially at larger reactions.
Long
we
mind,
might
that's
want
right.
that.
No?
Long mind at lunch.
So if not, more questions, I thank you again.